One reason we do observational studies and experiments is to get results and make conclusions. That making conclusions is what we call inference. Specifically, statistical inference means drawing conclusions based on data from a sample. There are two main types of inferences. One is population inference, or generalizability. The results basically seen in the data can be extended to the wider population. So if you do a sample and find that 40% of the people in the treatment group were cured from this drug, then we can make a guess that in the overall population it'd be 40%. The other type of inference is causal inference, or cause and effect. So the differences seen in the data were due to the group assignment. Cause and effect relationships can be drawn. Now, what we call scope of inference refers to the type of inference or conclusions that we can draw from the study. So does our study have population inference? Does it have causal inference? Does it have both? Does it have neither? The type of inference we can claim is the scope of inference. So, inferences that can be made about the population or cause and effect are determined by two factors in the design of a study. How the subjects were selected from the population and how the subjects were assigned to groups. In both cases, the most important part is whether there is randomness involved. So if the subjects of a study are randomly selected from a population, we can say our results can be extended to the overall population, assuming the sample is large enough. Once selected, if the objects are then randomly assigned to treatment and control groups, then we can claim causal inference. So, assuming again our samples are large enough, any differences between the treatment and control groups will even out except for the treatment itself. So if there really is a difference, it's because of the treatment. So, the difference between observational studies and experiments is that an observational study can have population inference if the sample is randomly selected, and well-designed observational studies will have it. The main reason we have observational studies, like do surveys and such, the main reason is for population inference. However, observational studies can never show causal inference since confounding variables can never be ruled out. Observational studies, the good ones, will have random selection, but no observational studies have random assignment. On the other hand, experiments could have population inference, but usually don't. And experiments will have population inference if the sample is randomly selected, but again, they often don't. Ethically, human experiments can only be conducted on volunteers. But the purpose of experiments is for causal inference. So experiments can have causal inference if subjects are randomly assigned to treatment and control groups, and a well-designed experiments will have that. Okay, let's take some examples. A dentist convinces some of his dental patients to be subjects of an experiment. Participants are split into two groups depending on whether they are currently taking at least 500 milligrams of vitamin C each day, and those who aren't. He then asks how often they have canker sores in their mouths. He finds that the proportion of those who take vitamin C daily and complain of canker sores is significantly smaller than the proportion of those who don't. So can this study be extended to the overall population? Well, he's convinced that some of his patients, so there's not really any random selection there. So this is non-random selection, not random. So no, this is not generalizable to the population. Can this study be used to show vitamin C reduces canker sores? Well, again, the split into groups is not random, so this is non-random assignment. It's just, he already asked if they're taking at least 500 milligrams or they not. The members themselves are separating themselves, so this is not random. This is not a random assignment. So what that means is this study has neither scope of inference, has neither population inference, nor does it have causal inference. Okay. Well, let's change this a little bit. A dentist convinces some of his dental patients to be subjects in an experiment. He randomly assigns half of them to take 500 milligrams of vitamin C each day and half to take placebo for 3 months. He finds the proportion of those who take vitamin C daily complain about canker sores is significantly smaller than those who don't. So in this case, again, there's non-random selection, so we don't have population inference, but we do have random assignment. So we do not have population inference, but we can talk about causal inference. So we can show causation, but it's not generalizable to the population. So there could be just something weird about this sample that we can show causation for them, but we can't necessarily extend it out to the full population. Okay. A dentist selects a random sample of dental patients in town and convinces them to be subjects in an experiment. Participants are split into 2 groups depending on whether they are currently taking at least 500 milligrams of vitamin C each day, and those who aren't. So, and he finds there's a difference in proportions between, with canker sores, between those who took the vitamin C and those who didn't. Okay. So, we do not have random assignment. They're split into 2 groups based on whether they themselves are doing the treatment or not. But we do have random samples. So the study is generalizable but cannot be show causation. There you go. Finally, a dentist selects a random sample of dental patients in town and convinces them to be subjects in an experiment. Randomly assigns half of them to take 500 milligrams of vitamin C each day and half to take a placebo for 3 months. He finds that the proportion of those who take vitamin C daily and complain of canker sores is significantly smaller than those who don't. Can this be extended to the overall population? Well, we have a random sample, so there's random selection, and we have random assignment. So this is sort of going to be the gold star because we have both. So this study is generalizable and can show causation.